Hello wonderful people of the internet, welcome back to another episode of Simuleo. So, we've got a lot to do today, and I kind of realized based on our schedule that we kind of set forth, there's a lot left to do before the end of the weekend. So I'm hoping that we can get everything we need to get done today so that we can just continue moving forward and getting our Fractal Christmas trees out by Sunday my time, which will be Saturday your time, and I'm hoping it's okay. Foldster, C252, thank you guys so much for coming in. I'm working on a YouTube video, should be done by tomorrow hopefully. Oh, just in time? Hey, Trash Talk. Just in time for what? Just in time to start the stream? If so, hey, welcome. Let me get a quick sip of water, and then we'll go ahead and talk about what we're going to do today. Oh, man. Super tired, as always. Okay, so let's talk about where we are. Let's CD into projects, Simuleos. That's not how you spell my name. Simuleos and Fractal. Come on. Shh, there we go, Fractal. One day I will be able to type, but that day's not today, which is a bit unfortunate. So let's go over here and let's just open up Mirage, Fractal. Not that one. Manypoint.png. Okay, so here's where our Fractal is so far. Honestly, it looks pretty good. I'm a fan. Yesterday we fixed up the problem where we were overemphasizing just random points on the edge of the universe, you know what I mean? So beforehand, we were just kind of plotting all the points and they were like very distinct. So let's see if we can, so like before, all of these individual points were being plotted. Now, we're only plotting the points that we need, which is a lot better in my opinion. It's a lot easier to see what's going on. So this is nice, because now we don't have all of this visual clutter on the outside. And I'd like to redo this heart animation later, once we don't have the visual clutter anymore. Maybe we can make it a little bit better. Anyway, this is our test fractal that we're working on, and I do think that we're making significant progress here. Now, the very last thing we need to do is basically implement a filter, which will make it so out here on the edges, we use a very large kind of Gaussian blur. But as we get closer and closer to the center, maybe in here, we don't blur it as much so we can see the fine details. Does that make sense? So here we're just trying to find a kernel that allows us to kind of take 10, 20 pixels or so in a row, blur them all together, and then as we get closer, as there's more points around the area, we don't blur them as much. So we're kind of working on that type of filter now, and this should allow us to create the crispest image we could possibly create with the provided information. And that will be the end of the Fractal Flame saga for now, and we'll start trying to draw our Fractal Flame Christmas tree, hopefully by the end of the day, and working on it mostly tomorrow. Then on Friday, we have to do some visualizations for the video itself, explaining how the Barnsley Fern works in general, and that should be most of the visualizations we need for the upcoming video. So I'm hoping it works out pretty well. I finally got my ML model to train by rewriting the entire thing to use a normal backpropagation net instead of a convolutional net. Oh yeah, fair enough. Nice. It's terrifying. It can tell the difference between a square triangle and a circle faster than any human. I think all people who will be out of jobs because of this. Oh man, I can't think of how many jobs I've had where I've just had to like differentiate between squares and circles. Oh man. Yep, my PhD is over now. Anyway, back to Fractal Flame. Let's see, shape predictor. Here's the source code. Yeah, I'll take a look. We're still kind of waiting for people to come in, so I don't mind. 1.png. Oh, okay. Yeah, fair enough. That's actually a pretty hard one to tell, too. I mean, like, I mean, I understand. Obviously, it's a triangle. But I mean, like, some people would look at that and say it's you know, a square. Other way around. Shapepredictor.py. Okay, so what am I going to do with my life? Let's go ahead and close that tab because I don't like that tab being open. Let's close that tab because I don't like that tab being open. Thanks, I'll take a look. Okay, so I think we're ready to go ahead and get started with the next bit. So here's what we're going to do. Let me go ahead and pop over here and let's go to the algorithm archive. Because of course, you know, when I don't know what to do, I just go to the algorithm archive and stare. By the way, we did recently change the algorithm archive. So now all the videos have all the chapters. So for example, this is a chapter on Monte Carlo where you can change the language and all that kind of stuff. Also has my YouTube video now embedded into the chapter. I understand that some people might be against this, but I think it's probably a good idea to do just to kind of I don't really know the best way to put this, but to kind of synergize between all of the different social media platforms we have. Because if the channel succeeds, the book succeeds, so on and so forth. So there's no reason not to do it. And so for basically all of the videos that I have, I put them into the algorithm archive. So here's another one. I didn't put it for gift wrapping, but I did for FFT, stable marriage, for example, all these guys. If you want to input your own drawing, you can just pass a file as a command line argument to test.py. Oh yeah, fair enough. Let me go ahead and get a quick sip of water. I should probably try it out, but I'll look at the code later. I don't know why I'm so thirsty. Like literally, I'm sorry about that. That was very loud. We just started streaming, and I'm already like a third of the way through with this water bottle. I don't think it's gonna last much longer. Okay. So what I'm gonna do now is go to Gaussian elimination. No, that's not what we're on. What are we doing? We are doing convolutions. There we go. So I basically took this convolution code that we had over here and extended it to 2D, which is what we'll be working on today, and added some slight variations to it to basically write down the pseudocode that we need for stream today. And I know what you're saying. I know that, you know, usually I don't write pseudocode out before stream, and for a lot of people, the process of coming up with the code is a very enjoyable process. But this was a situation where I just wanted to make sure I got this right, and I didn't spend forever fidgeting on it, because I'll be honest, there's a lot that we need to get done this week, and so I wanted to make sure we had everything ready to go. Sorry about that. So here's a pseudocode for what we need to write down today. It's kind of sort of large. I don't know if you can see it or not. Yeah, you should be able to see it just fine. So there's a pseudocode for it. It's about a full page of things that we need to get done. So I'm pretty sure we'll be able to figure this all out. And it wasn't like exactly rigid pseudocode either. It was just kind of like, hey, this is kind of sort of what we need to do. Oh man, I'm super yawny, sneezy. Everything's just like weird today. Command prompt, yeah, it's programming time. So I was in the elevator the other day, and someone was just talking about how every time they do programming, they need like food next to them or something like that. I don't know, like, does everyone else have a similar, like, I mean, not ritual, but I think, you know, there's this kind of stigma or this idea that a lot of programmers, they'll have like Mountain Dew and, you know, chips next to them or something like that while programming. And I don't know if this is what people typically do or if I'm the weird one here. I just basically have water, and I don't usually eat too much when programming. Like usually when programming, I get to this stage where I don't know how to put this, but like you get really absorbed into programming and you just end up not eating anything. It's kind of the same for video gaming sometimes. You know, you're just playing so much in terms of video gaming that you just kind of, yeah, maybe it's for gamers, but yeah, you just get so involved into the game or into the programs that you end up just like working, then you look up, it's like, oh, it's been 2 hours, and then you just keep working more, you know? I don't know, it happens sometimes, like not all the time, but sometimes, you know? Hey JSPP, how are you? I'd really like a cup of tea next to me. Yeah, that's fair enough. It just depends on the person. So I'm going to go ahead and open up a Julia prompt over here. And I'm going to go ahead and start. So let's go into VIFS.jl. I also wrote part of the script for the video that's coming up. And like I said, I want to spend Friday basically working on some animations for the video. So I'm hoping that on Thursday, we finish up all of the, we finish up the Christmas tree that we're trying to draw, the fractal Christmas tree. And then hopefully on Friday we can get the animations done. They're pretty simple animations. Basically it's an animation of the Barnsley fern itself. I'm just going to be taking a random distribution of points 4 times, but I need to show the random distribution of points being like generated on the fly. So we generate the random distribution of points, and then we show what happens when you transform them with each branch of the Barnsley fern. So let me just go ahead and here and look for Barnsley. Here we are. So if you notice that each point in the Barnsley fern, basically it has 4 branches. It's got 1, 2, 3, and 4, and there's a probability to choose each of these guys, right? And so this guy right here is basically a matrix transformation 0000.16. And so the idea here is that after matrix transformation, you have some point that you're multiplying by this matrix, and you're basically multiplying the y position by 0.16. and the rest of the point doesn't matter. So this is basically the initial stem, the stem that goes in the y direction. And then each of these other branches all correspond to something different. And so if we take a random distribution of points and we transform them with these matrices, we should kind of sort of see what part of the fern each of these individual components are drawing. You know what I'm saying? So I want to just very quickly show this visualization, be like, hey, this is kind of what we're doing here with the Barnsley fern. And at the start, I want to mention, ThinkerCon, be like, hey, during ThinkerCon, I had the opportunity to meet with Dan Schiffman from Coding Train. He was an amazing person, and we did a live coding competition or challenge together where he made the Sierpinski triangle. There's more information on what he did here in his video. He also took it a step further, and so I kind of wanted to take what we did a step further. So here's what we generated during the, oh, actually, let me show that to you guys. So here's what, I'm going to show you guys what we generated during the ThinkerCon, guys. So let me go ahead and do git pull origin master. Again, before Simulators, we have a messy directory. So vi barnsley.jl. Oh, I guess I already had this in here. So let's just go over here. Let's do include barnsley.jl real quick. Give this guy a go, and then I'll show you what we did during ThinkerCon. Does Julia stand for James's Ultra Legendary Incredible Archive? No. So here's what we did during ThinkerCon. So let me just do a quick new plot. Barnsley, no, I think it's plot Barnsley.gp minus. So this is what we generated during ThinkerCon. It was just a Barnsley fern, and it basically just changed color with time. That was all we did. He, of course, generated the Sierpinski triangle. Now, you might notice that as we're generating all these points, it kind of like slows down with time, like the colors, but yeah, this is the fern that we created. I thought it was pretty cool, and kind of the reason why we wanted to do, or I wanted to do a Christmas tree type of thing is because I wanted to, I don't know, basically redraw this Barnsley fern in a better way. And so the first thing we can do is we can pretty straightforwardly shift this such that the Christmas tree is all like straight, you know what I mean? So that like this guy right here is over here. So we tilt it so it's this way. That's easy enough to do. There's no problem with that. All we have to do is change one of the matrix transformations. Then after that, we have something that kind of sort of looks like a Christmas tree, but I wanted to do something slightly better. So that's what the whole Fractal Flame is. Over 900 stars on GitHub. Yeah, the algorithm archive has been growing. It's pretty good. I'm a pretty big fan of that. So yeah, this is my attempt at a Christmas tree during ThinkerCon. It turned out, I mean, I'm pretty happy with it. So now this might be actually the best Christmas tree we can possibly generate. I'm not gonna lie, I'm not too convinced that we can actually do the Fractal Flame thing to make it look better than this. So I hadn't started the algorithm archive. Right, 901 stars on GitHub. Or, maybe not. But yeah, so this is what I did during ThinkerCon. I was a fan. I think it turned out pretty well. Oh, hello, new plot. Never mind, don't worry about it. Alright, so, it's gonna keep, yeah, dagnabbit. Yeah, so anyway, it's pretty good. I was a 906 star. Aw, man. So 906 stars on GitHub. It's pretty good, though. I'm a pretty big fan. It's kind of telling me that the algorithm archive does have a future. We just need to keep pushing it, and I think the more we push it, the better we're gonna get. I'm pretty excited that I like that number because it's the same upside down and backwards. So you're specifically waiting for that number. I understand. I totally understand. All right, so let me get a quick sip of water again. Getting down to half this liter of water in 15 minutes. You're right, Gitbook is pretty hacky, but that's a huge project that I kind of want to leave to the future, and I think I would also like to try my hand at, but only after I'm working on this project more or less full time, because at this point it's I just don't have the time to do it. You know what I mean? And we're so far behind on everything else. It just doesn't make sense right now to do that. So anyway, so the whole story is, at ThinkerCon, we made this tree look kind of like a Christmas tree, so we wanted to do a Christmas special where we tried to use the Fractal Flame method, which is this really cool method to generate a cooler Christmas tree. And even if we fail, it's still interesting to talk about how this method works and stuff like this. So I think it's pretty cool. Okay, so let's see what we got here. I think he stopped developing though. Nev apparently got a sort of working version. Oh yeah, that's true. That's true. I don't know where it went. So we'll work with what we have. I think in maybe a month or two, we'll check back in. Again, like I said yesterday or something like that, and I know I've said this many times before, but 2019, I really want to start putting content out more regularly on my YouTube channel and stuff like that. So I don't know how to do this, but I'm really going to be trying in 2019 because I definitely want to get more content out. Where are we? Here we are, density estimation. That's what we're looking for here. So the first thing I'm going to do is I'm going to read in a separate, like, kind of fudge factor, and I'm just going to call it fudge. All right, and this fudge factor is going to be, I guess we'll say it's a float 64. But in actuality, it's probably going to be an integer. Basically, the point is here, we need some sort of variable that allows us to slide our filter. So like I said before, what we're doing here is we're creating a filter such that it smooths over areas that have very low density, and it doesn't smooth over areas of very high density. So what we need is the filter size, how big the filter is that we're dealing with here. And then we also need some sort of factor that allows us to more or less smooth over areas depending on this factor, right? So like we could want to smooth over certain areas a lot more than other areas. So we probably want to make sure that, you know, we have this factor set such that it's relatively straightforward to modify. Let's see. I haven't seen him in Discord in a while. I guess check their code out. Yeah, that's true too. I don't know where they've been recently, but that's perfectly okay. I mean, it doesn't matter so much. Okay. Well, I mean, we'll figure it out. So first things first, we're going to create a temporary, I called it P. I don't know why I called these arrays P. I think maybe points or pixels, probably pixels. Anyway, we're going to create a temporary pixel array here, which is going to be equal to the size of the previous array with the filter attached to it. Now what we're going to be doing here is we're going to be having a standard filter size, but what we're going to do is we're going to modify kind of the Gaussian within this filter size such that it's very large when we have fewer points and very small when we have a lot of points. I just hit the microphone and I apologize for that. He's still a member of the Discord server, I just checked. Cool, I mean, we can take a look at that. But again, I'm not able to look at it right now for like a month or something like that. So maybe we should not follow it up so much. For I is equal to, I guess here we're just going to be going to 1, 2. And then I guess it's going to be ptemp. What is it? It's going to be size of ptemp. 1 second, I can type of ptemp. And then we're just going to grab the first row here and there. And then we're going to have another one for j is equal to 1 to size of ptemp. And this is going to be the second dimension. So one goes through the rows, one goes through the columns, and here. Okay, so now we're going to go through each individual pixel in the new image that we're creating. And we're going to basically create each pixel, right? So now the trick is to create basically a start and an end point for basically... I'm going to explain this in a better way. Let me go and open up Zernal. Okay, I think I can draw on that there, but can I draw on that here? That's a good question. I cannot. Try it again. Discard. Okay. So what we're doing here is a basic two-dimensional convolution, right? So here we're going to have our image, right? And this is going to be a whole bunch of different pixels, right? Okay. So let's say we want to generate this pixel right here. Well, what we're going to do is we're basically going to take our filter, which we'll say is maybe this big here, in blue. And we're basically going to multiply the filter by this element, this element, this element, all these elements here, and sum them together for this element here. Does that make sense? So what we need to do is basically go through our two-dimensional space. And then after going through our two-dimensional space, we need to basically input this filter into each each pixel for our new image and all the surrounding pixels, depending on how large the filter size is. Now, the filter size is variable, so we have to basically create our start and end point on the new pixel image. We need to figure out which pixels we're actually dealing with here. And then we go from there, right? So after we find our start and end point, we should be okay to iterate through these points in our code. And that's kind of what we're looking for next. So next we're looking for a start and end point. And I'm just going to create basically an XY vector for start and end. So let's see, what do we have here? What do we have here? Does anyone know what the compiler bot is on the Discord server? Wait. I don't remember what the compiler bot does either. Honestly, I don't remember it at all. Hey, Make, what's up? Let's see, credits. 8,700 credits. Okay, so here we have the two loops. So in here, we're just going to go ahead and create our start and end point. So we're going to say start is going to be equal to, and I believe I can just do the following. So we're just going to say this is going to be equal to I minus filter size. Filter size. Times 0.5. Right. Now the thing is, I think we want to make sure this is integer division. So let's just go ahead and divide by 2. Okay. So that's going to be the first element. And then the second element is going to be j minus filter size divided by 2. Okay. And we're going to do a similar thing for the endpoints. So here we're going to do end. It's going to be I plus filter size over 2 and j plus filter size over 2. Now there's some limitations here that we're not allowed to work with. So basically if we're going to say start, I guess it's going to be start of 1 is less than 0, right? I'm just going to put a bunch of if statements in here. Then we're going to say start of 0, start of 1. Equals 1. I guess it has to be less than 1 because of the way that Julia does the notation here. So we're just going to have to do this for start of 2, too. So yank 3 yank. Basically a bunch of if statements to make sure that these are in bounds. Start of 2, 2. I missed a lot of stuff over here. Oh, this is just a bunch of credits. Let's see. Goose and Geese, your question got recognized. Why not randomly select a pixel order? Wait, what do you mean, why not randomly select pixel order? I'm unsure I understand what you mean. Let's see. You've never seen it online. It's just called a compiler. Yeah, I'm not sure what this bot does either. I mean, there's a lot of credits in here. I'm having trouble following the chat. I don't know how that works anymore. Let's see, credits. You don't have enough for that. Oh yeah, okay, so I think I got everything that's not credits, but if you have other questions, just please feel free to ask. So let's go and do yank 6 yank, paste it down here. And we're going to be modifying the endpoints too. Actually, yeah, end is, we'll say greater than, and this has to be, 1 second. Is this x dimension? I'm going to say p of, yeah, it's got to be p, so size of p of 1. And then we're going to say end of, it's going to be size of p of 1. Just do yank 3 yank, paste down here, d3d, and we're going to say end of 2. Let's see, what do we have here? Let's see, 100 credits. Wow, I got wrecked, but I know the syntax now. Fair enough. That sounds like every programming challenge I've ever done. Okay, so now we have basically the start and end points on the image that we're working with here. Hey, Gathros, how are you? Let's see. I'm sorry if I missed you earlier. There was a lot of roles and stuff in the chat. So we're going to say we have some sort of sum, and this is going to be equal to 0. And we're just going to sum through our two-dimensional space here. So we're going to say 4. And I'm just going to use L and M. I realize that maybe this isn't the best way to do this. 1, 2, I'm sorry, it's going to be equals start of 1 to end of 1, right? And here. And this is also like horrible complexity. Like, I also understand that. For M is equal to start of 2, end of 2. What do we have here? Fair enough. The duels are there's a lot of duels in the chat, so if I missed anything, just let me know. So we have M equals here. And basically what we're going to do is we're going to say mod privileges. Welcome to the chat. Oh, wait. Wait. Mod privileges help you out here? Okay, so we're going to say sum is going to be plus equals whatever our signal is, which is going to be our pixel array, P, of LM. Now, I always forget how to do things in Julia, so let's just say J A is going to be equal to 1, 2. Okay, 2 element array. So let's say 1, 0, 2, 0. All right, and we're just going to say A of 1, 2. Yep, that seems correct. So we're going to go over here. We're just going to say LM. All right, and I think it should be, is it row first? Row column. Let's do 2, 1. So that should be the second row first column. So this should be the X, Y. Yep, this is correct. LM. So plus equals LM. And now we have our sum that we can work with in order to generate our basically Gaussian, I guess, signal that we're going to be working with. So now we're going to have to define the signal itself. And I think what I'm going to do here is I'm going to create a separate function to do so. So we're just going to say define Gaussian. How about we just call it define signal? How about filter? Something like this. And we're just going to read in the sum. Then we're going to read in the filter size. And the last thing we need to read in is our fudge factor. Okay? And in here, I guess we're going to say filter is going to be equal to this. So we'll say filter is equal to that. Oh, hello there. You. Filter is going to be equal to this. Great. So now we have the basics getting started. So let's go ahead and use this define filter function, or create this define filter function. And up here, so we're going to say this defines a filter. It's easy enough. Let's just say function. Define filter. Okay, and it's going to read in a sum, which is going to be, I believe, an int 64. So we're going to say sum int 64. Then it's going to have a filter size, which is again going to be an int 64. And then the last thing we need is a fudge factor, which I said it was a float 64. And I guess that's fine. So we're going to say fudge. But honestly, I think this is also going to be an int 64 based on how I have it written down in my notes. So maybe we should change this to an int 64 also. Yeah, we'll change this to an int 64. Okay, what do I have in the chat over here? Let's see, we've got a bunch of duels. Welcome to chat, mod privileges. Let's see. AC252. Challenging to a duel. Who can ban faster? Please don't start banning my entire chat. Alright, so we have the fudge here. And let's just go through and define this. So we're going to say... so the filter I always want to be square, so I don't mind this so much. We're going to say... filter is going to be equal to zeros, filter size, filter size. All right. So now we have that. We're going to say basically for I equals 1 to filter size, and then we're going to have a similar one for j is equal to 1 to filter size. And there, and end here. All right, we're just going to go ahead and define our Gaussian. So we have to create an x and y coordinate. So I guess we're going to go up here and define x. And x is going to be equal to, in this case, it's just some boundary Can you ban me? I don't know if you can. It's some boundary. No, I think I'm okay. So actually, it's gonna be some boundary between C252. You're just like, I want to ban myself. That sounds fun. All right, so X is gonna be some like, is gonna have some boundaries between. I'm just gonna put it as like -2 and +2. Nothing crazy here, just some sort of physical boundary that allows us to choose between like some sort of space. So we're gonna say X is gonna be equal to -2 plus 4. And I guess I should do 4.0 just to make sure this is double. 2.0 plus 4.0 times I. And then we're just going to divide this by filter size. Now, the issue here is that we have a lot of integers, so I want to double check something real quick. So I'm going to say over here, I is equal to 1. And now I just want to do 1. How about I is equal to 10? And we're going to do 1.0 divided by I. Yeah, okay. Just making sure we're not doing something dumb here. Okay, good. So this should change this to double space. Now we're gonna do a similar thing for y. So here's our x position, and let's go ahead and do a similar thing for our y's here. So it's gonna be our y, and this is gonna go through j. So now we have some space going through. Oops. So now we have some space in the x direction and some space in the y direction. And now we're just gonna define our two-dimensional Gaussian here, depending on our x, y location. And this should be relatively straightforward to do. So we're going to say filter. Let's see. Filter of, I guess it's going to be I comma j. It's going to be equal to, again, it's going to be something like 1 divided by 1.0 divided by, let's go ahead and define a sigma first. It should probably be sigma squared. So we'll say sigma 2 is going to be equal to, it's going to be our fudge factor over sum. So it's going to be fudge. And I guess I should interpret one of these as a double. So we'll say, I don't know how to do that. Float 64 of 1. Okay, so let's try that. Float 64. Filter. Oh, I'm sorry, fudge. And then we're going to divide that by float 64 of sum here. And so here what we're doing is we're defining some sort of variable width of our Gaussian depending on the number of points that we read in. It's inversely proportional to the sum that we have, and we're basically putting in a fudge factor, right? So the idea here is that we say, hey, maybe our fudge factor is like 100 points, right? And so this means if we are under 100 points, yeah, under 100 points, then our Gaussian filter is very large. But if we're over 100 points, then it shrinks. And if we have like 1,000 points or 100,000 points, then it's like basically non-existent, right? And so that's kind of the hope here, that we have a non-existent filter where we have a very high density of points and a very large filter where we have a very low density of points. So we're going to have to manipulate this fudge factor such that it is relatively close to the number of points that we're reading in. What do we have here? Am I banned? Yes. I am missing a lot of chat here. Let's see. It must be confusing not knowing yourself. Wait, what? What? I don't know the user bought cake. All right, so we can say the filter. And here we're just going to do 1 over, typical Gaussian stuff. So it'll be square root. All right, I'm having trouble finding a place to put this piece of paper. So 1 over square root of sigma 2, because it's always sigma squared, times 2 times pi. So we're going to do the 2 pi over here. So it's going to be 2 times pi times sigma. Ooh, hello. 2 times pi times sigma squared. And the parentheses here. Check to make sure this is the right parentheses. It is. And now we're basically going to say E. Then we're going to do times exp 2 the negative x squared. Now my question is, how do I do a two-dimensional Gaussian? I don't really remember. Is it just x squared plus y squared? I believe it is, so we'll try that. So we're going to do x squared plus y squared, and these should be minus x squared and minus y squared. So do minus y squared, and we'll do minus x squared. We'll put these guys in parentheses here and there, and then we have those guys in parentheses, and yep, that should be okay. Divided by 2 sigma 2. So we're going to divide this by 2 times sigma, oops, we've put those in parentheses, 2 times sigma 2. And I believe that should be basically our Gaussian done, right? So we have some sort of exponential that's dependent on x squared and y squared. These are both negative, and this should be about right for our filter. Okay, so now we've defined our filter here, and we're just going to go down here and say return filter. All right. So now we have our filter defined, and basically what we have to do is go through, multiply all the appropriate points, and go from there. The duel between Gathros and Vodacake timed out. It's fair. No one ever watches the stream. It's okay. Okay, so we're going to go through and define our actual element here. So we're going to say we have the filter defined, and we're going to say the element. So this is going to be the individual pixel, the pixel value that we're working with here. It's going to be equal to 0. We're going to say for, again, using the same notation as before, L is going to be equal to start of 1 and end of 1 and there. And we're going to say for M is equal to start of 2, end of 2, right? And end there. So this is the pixels on the image itself, right? But we also need a second loop so that we can pi equals 3. It's pretty close to 3, but not quite. I think Julia definitely defines pi as 3.14159, whatever. Okay, so let's see. We are going to be going through this too, but what I want to do is I also want another counter j that just counts up or down, right? No, sorry, it's... Oh, you're just going to put down the whole? It's false? Pi is false? All right. Tavera, you're on your laptop. Wait, come on. You can definitely read this on your laptop. Like, I read it on my laptop all the time. Pi divided by pi times 3 equals 3. Oh, that's true. That's definitely true. Yeah, so yeah, I really can't change the font size, though. I mean, the font size is what it is. I don't think I can make it any bigger than this. Without making it like completely impossible for me to actually do programming. I mean, granted, I could do a second screen and put like the compilation terminal on like the side screen or something like that. There's probably a way to manage that. But that's we'll see. We'll see how to do that. Okay, so what I want to do very quick is say for. No, you don't have to go to your desktop. It's fine. There's no big deal. So we're gonna say for ij equals, let's do 2 through 20. Okay, so that doesn't work then. So I'm just gonna go ahead and create. There's a way to get this done. I just don't know what it is. So I'm just gonna say. There definitely is. How do I do this? For loop with multiple variables. Julia, let's see what we got here. Your second screen and move your face to the top of the chat. Wait, what? Twitch needs multi-screen support and a minimum resolution just to annoy the plebs. Yeah, I mean, that's not what I'm trying to say here. It's that I'm running out of space on my screen, you know? Like, this is already very hard for me to code in because, like, I'm used to having at least 4 terminals on screen to work with at any given point in time. So, like, I'm always, like, flipping between different terminals, and it's kind of hard to work with. You know what I mean? So I really would like more on the screen, but I just can't do that without, while people can still, like, look at the screen and stuff like that. You know what I mean? My laptop has a super crap screen. Yeah, fair enough. Twitch needs multi-screen support and minimum resolution. Sorry for the yawn. It doesn't matter. I mean, it's not really that hard on chat, or it's not really that hard on me at all. iPhones, I didn't realize it was 2010. Hey, that's your fan. Thanks for coming in. Also GDE, thanks for coming in too. Okay, let's take a look here. So I'm just gonna look for some for loops over here. For nope. For loops and iteration. That's what I want. All right, so I want nope. Dang it, nope. That's not what I want at all. I want multiple variables. I want iterating through I and j at the same time. But I don't think it'll allow me to do that. Or rather, I don't know what the notation is. So we're going to do this in a dumb way. Let's go. So we're going to say, over here, we're going to be saying that I1 is equal to 1. And J2 is equal to 1. I2. Let's go. So here we're just going to be saying, actually J2 plus equals 1. And then here we're just going to say J2 is equal to 1. I2 is equal to 1. And down here we're going to say I2 plus equals 1. Okay. I know this is dumb, but whatever. It is what it is. Let's see. Care all you like, you won't hide your data from me. He doesn't care. Have 2 keyboards and a hoodie. Certified not a hacker. He doesn't have 2 keyboards and a hoodie. Yeah, I don't know anyone that has like 2. Well, okay, no. Actually, I have multiple keyboards at my desk. Let's see. Care and privacy is a pretty common thing. Let's see. I mean, yeah, that's totally fair. And not saying catchphrases like, and I'm in. Best green tech stories. Go. Let's see. Do sunglasses help with oh no, where are my sunglasses? Oh, they're out there. I was gonna ask if sunglasses helped with the hacker image, but I guess it doesn't, especially because I can't find my sunglasses right now. They're over there. Okay, so we have J2 plus equals 1. Let's go ahead and do it here. And what do I do? So what I need to do now is basically say that each individual element, so the element is going to be plus equals signal of LM, where the signal here is going to be the P of LM. And I believe I need PLM.val, because I think I've been ignoring that so far, times filter of I2, J2. All right. And that should basically be it. And so let's go up and let's just make sure that when we're adding these guys together, we're doing p.val, which is the value. And this should basically do it. So we should have ptemp defined now by just going down here and saying that ptemp of ij is going to be equal to element. Okay, so now we have the ptemp, and the last thing we need to do, which I didn't write down any notes for, is stripping the excess here. But I think that should be relatively straightforward because we're basically going to be saying that p is going to, all the p values are going to be a subset of all the values we have in our ptemp. So all we're going to have to do is say that for, oh, hello there, move over here, for I equals 1 to p size, 1 second, of p of 1, and there, and we're going to say for j is equal to 1 to size of p of 2. And I realize this is horribly not optimized. I get that. We're working on it. Hacking simulators, beep boop. That's fair enough. What do we have here? Let's see. I have 2 keyboards at my desk. I don't have my hoodie. I have 2 keyboards, but one is broken. Hey, did you remember me? I do remember you. How are you, man? I feel like it's been a while since you've been on stream. Maybe a month or 2? I'm not sure, but I know you've been here at least this year. So you're not super old. Let's see. Is this a La La song? It was a La La song. I'm sorry. It's gone now. The song is now gone. Okay. So here we have this. What I'm going to say is... Oh, what? Oh, no. Oh, no. I'm off a space. All right. So we're going to do P of... Yeah, this is what I need to do. So it's going to be P of ij dot val is going to be equal to ptemp of I minus filter size over 2 j minus filter size over 2. Yep, that should do it. And then we just return. No, that should be correct, assuming we modify P. So let's just return P. Actually, maybe we should return P temp? Or we just define P2. And we work on P2 all the time. But no, P temp. Let's see. What do we have here? Dang, it feels good to be a gangsta. Okay, fair enough. I need to change that comment. Let's see. Now that I know the means induction. Oh, I'm great. I'm 15 and got remote internship. Oh, cool. We have been mailing with the company for a while today, and I've joined their Slack team and got a project to develop. Oh, that's super cool. At 15, that's amazing, actually. At 15, like, I think I was just learning how to program. Like, I knew nothing. So that's a very good opportunity. I'm actually I'm very impressed, actually. Whenever someone starts using BotterCake, the whole chat gets derailed. It's fine. It happens. That's the nature of BotterCake. So I think this should work okay. We'll see what happens. What I'm going to do is the density estimation, and I'm going to hope that after density estimation, well, actually, let me just run this real quick. Let me just make sure these functions actually compile. So we're going to move over here, and we're just going to do include ifs.jl. And we're just going to make sure I don't have a syntax error, because I probably do. And as long as this works okay, actually, I guess I don't have a syntax error, then, oh, we do. Nice. Oh, okay. Let's go to 163. Okay. The issue here is that it doesn't like me calling this an endpoint. So let's say end points and start points. PTS, I guess we'll call it. We'll just add an underscore PTS for all of these guys. Now PTSD, that's a different thing. Here, there. And start point. And point. And same thing down here. And there. Oh, oops. There. Oh, dang it. Nope. There. Gotcha. Okay, so let's try this. Make sure there's not a syntax error. Premature end of input. Let's go to 150. What? How is there a premature end to the input? Okay, let's take a look. Everyone's 15 here then? Oh, huh. Interesting. Let's see. Also 15. Oh, interesting. Let's see. Everyone 15 here. A Python programmer program using block scores API C252. Huh. Yeah, that is quite cool, actually. Yeah, that's like way ahead of where I was when I was 15. So that's a super good, or that's super interesting, is what I'm saying. Like, good job. Okay, so I seem to have missed an end somewhere. If this was C++, it'd be super easy to find it. But in Julia, that is not true. Did I do the for loop wrong? The for loop should be right. Okay. It says syntax incomplete, premature end of input. Okay. What is your deal? It says expression starting on 150. It's gonna be really hard to find. Holy cow, function density estimation, P array pixel 2, filter size int 64. What does that... Maybe this is a different error than what I'm thinking it is. Let me just take a look at this. It says load error, incomplete premature end of input. Let me see if I can find more information on this error. Binary compilation, load error, premature end of input. Maybe this is okay. Let's see. Let's see, that's because type is a preserved keyword for defining struct in Julia 0.6, and before is deprecated in Julia 0.7. So Julia version 1.0, there is no error. There is an error. Ah, the point is that is produce error, load error, invalid, syntax incomplete, stack trace, and the message one normally gets. As you say, the same thing is fine. Don't just Let's see. All right, this is not helping me. Let's see, what do we have here? Did you say you were able to program with 15, at 15? Never mind, my comment then. Yeah, so at 15, I was programming in C++. This was the first programming language I learned, but then I had completely forgotten everything about it after that. Like, basically, I learned it when I was 15 or so, and then I didn't do anything with it. So, you know, I kind of forgot. So maybe this isn't a problem with it ending. Maybe this is a problem with the function itself. So we have defined filter up there, sum in 64, array of pixel 2. What is your problem? I have no idea what this problem could be. I mean, it doesn't matter. Like, the thing with programming, right, is it's not like people are better than other people, you know? I mean, that is true. There are people who are better programmers than other people. But the thing is, as long as you're trying to get better, like, and you're not just content with your ability to program, you will improve. And that's the main thing. Like, just take the time, don't look at other people, you know, don't say, hey, that guy's way better than me. Just say, hey, look, trying to get better. And, you know, just do your best to improve. This is true for most things. I know it's kind of generic advice, but just, you know, don't discount yourself is basically what I'm saying. Oh, this might be the problem. Maybe I shouldn't have been using C-style syntax for all of these if statements. Maybe I should have been using Julia syntax for all of these guys. I don't know. We'll try that. All right, and here. Oh, I see the problem. All right, let's see what happens now. Hopefully this compiles and works. The company has an office in my city, I guess, but they didn't tell me that you need to go there. Remote working. Oh, nice. That's even better. Honestly, I've always wanted to work remotely. Oh, cool. So this code seems to run. So now the question is, does it do what we want it to do? That's a very good question. So let's go ahead and try that guy out. I'm starting to use Scratch for 3rd grade. Not really a programming language, though. I started using Scratch in 3rd grade. Oh, yeah, but, I mean, we teach Scratch. Like, it's one of those things that I think is actually a much better programming language than people give it credit for. So what we're going to do is we're going to go down here, and we're basically going to add the density estimation. Where do we rate the image after here, so let's just do density estimation. All right, and we're going to do density estimation of, what are we actually calling these guys? Pixels? With a filter size of, we'll say 10. Yeah, we'll do 10. And then after this, we'll do a fudge factor of, we'll say 100. Just as a quick guess of what everything could be. So we're going to run this now. And hopefully it works. This adds a lot of complexity to the code, so it should take a bit longer to run. But if it runs and it outputs an image, I'm pretty happy with that. Argument error, invalid index. What do we have here? To index flame 343. Okay, so then it says 336. All right, and so then it is 173. Sum equals 0. 0.0. That means that this sum is always a... Is the value always a float 64? Oh, it is a float 64. So now we want to go down to 173. Let's see, so we have sum.val, sum is equal to that. And so now what I want to do is when I call the this function down here, we want this to be a float 64. Which is great, because that means we don't need this float 64 here. Okay? And then we have the filter, which is going to be defined as 0 as a filter size, and that should be naturally floats. So I'm not too worried about that. Go and write this, go here, and let's include that. My mother is a Persian Turk? Huh, okay. I'm from Turkey and English isn't my main language, so I'm sorry if I've had any mistake. No, it's no problem. 1.0 flight, wait, this is the same issue we had before, isn't it? Invalid index 1.0 of type float 64. Yeah, it's supposed to be of type float 64. Okay, let's see, what do we have here? It is again on 173. That's the issue. It's going to be sum plus equals p of lm.val. Is this because the start points and end points are for some reason floats? Let's output L and M real quick. L, M. Does this work? Give this guy a second to go. All right, so hopefully 1.0, yeah, why are these floats? They shouldn't be floats. This should be integer division, right? So let's do, filter size is a float, so let's do 10 divided by 2. Why does it, so we have to do 10 div 2? All right, that's what I want then. So we're gonna want to do here div filter size 2 for all of these guys, and this guy over here, there, and here, and let's just add a div up here. And there. So basically I'm forcing integer division here because Julia naturally assumes floating point division. And then that should hopefully solve the issue. Let's see, what do we have here? What am I missing? 10 by 10 float 64 at index 111. I guess we're going to have to do a -1 here at the endpoints, right? Where's that? Here and there. All right, let's give this a guy a go. Hopefully this is okay. Wonder how fast Scratch is. Scratch isn't too fast. I mean, I'm pretty sure Scratch is quite slow. It's even slower than MATLAB. Argument invalid index -4.0 of type float 64. All right, where's this guy? 194. Okay, so we're saying for size, J, oh, okay, I see. Because this should be P temp minus filter size over 2. These should be, it should be plus filter size over 2, actually. And this again should be div here. So we ensure floating or integer division, and we're going to do again div filter size divided by 2 and plus here. Okay, work. I'll catch up in chat in just a second. Wonder how fast Scratch is. It's not very fast. I believe Scratch is about 5 times faster than C. Yeah, it depends on whether you're using the Fortran compiler or not. Because Python is pretty slow. It is slower than Python. It definitely is. Faster than the speed of light. Yeah, but speed of light's pretty slow. Ooh, it worked. Okay, nice. We'll take a look at that. About everyone can do programming. I want to slap Bill Gates for his advert, everyone can code. Really look at few streams on Twitch. Some are just random going into something without learning the basics, without having the logical thinking. I'm never going to draw like a person who has some kind of drawing inclination because my mind just doesn't work that way. Like others are not inclined to work with imaginary abstractions. So as far as that's concerned, Radu, I genuinely do believe that anyone can code. I believe that everyone can code. I really, really do believe that. But it's the same thing as any other creative endeavor. Painting, writing, whatever you're doing. Music, you got to put a lot of time into it. You can't just start coding. You have to learn to code. You've got to learn to be creative. This isn't something that you can just do naturally. I do genuinely believe that everyone can learn to code. But you got to work hard for it. It's just like painting. It's just like any other artistic form. You got to spend your time learning the guitar. You got to spend your time learning whatever it is, and sometimes it takes a lot longer for some people than other people. Like, I know for a fact I'm crap at music because I have no musical inclination, but I know I could still learn if I wanted to. It's still there. Like I still could become good at music if I wanted to. I know that's very vague, but it's possible. And so that's just what I want to say. It's late here. Yeah, so that's kind of where we're at there. I feel like I missed something. I missed a lot of chat. So if you have questions that I missed, please feel free to just let me know. Everyone can code. Question is, does it actually do something useful? Is it still in the debugging stages? Oh, this is true. Nobody works hard and then look 10 years experienced developer. This is true. Like, you can clearly tell how much effort someone has put into programming based on how much programming they've done. You know what I mean? Like, it just takes time. You know, you can't just expect to be good at programming immediately. It's I guess in a way different than art or different in music in that I don't think anyone is naturally good at programming. Like, you don't just naturally like start coding. It's like, oh, I'm very good at this. It's like, it takes time. Like, it takes time to learn the basics. It takes a lot longer to figure out what it is that you're doing. Creatively expressing yourself in code is one of the most difficult things, I would say, difficult parts of programming. But once you can do that, once you can kind of look at code and be like, oh, okay, I see what's going on here, then you get pretty good. And that's what I'm saying. Like, I think you're right in that maybe the everyone that learns to code thing, like, or maybe the everyone should code phenomenon maybe was pushed a bit too far in some ways. In that I do believe maybe it's a little bit harder to learn to code for some people. But generally, I do believe everyone can learn to code if they put the effort into it. Let's see. Yeah, but nobody works hard and then looks like a 10-year developer. Everyone can code. Question is, does it actually do something useful? That's another bit of another discussion. The only reason I can program is because I've practiced every day for quite a while. Yeah, everything is just a question of effort. The problem is no one wants to pay the toll. If you want to cross the bridge, you got to pay the toll. Yeah, that's fair. Do you know of 10,000 hours rules? It was the topic of a TEDx talk, I guess. You ought to watch it. Oh yeah, the fact that if you work 10,000 hours on something, you become an expert in that thing. Anyone can learn to code. Let's see. You can't just learn to program in a month. That's also true. In programming, you also need to learn a crapload of concepts and conventions, and you need to be able to apply them. Yep, it's a language like any other. You wouldn't learn Russian overnight either. Yeah, this is true. I genuinely do believe that anyone can code, but you guys are right in saying that maybe there's a lot of boilerplate there. Okay, so let's take a look. All right, I think I just made it darker. No, I think I changed the gamma factor. Let's go back here and let's try changing the gamma factor to 2. And let's try running this guy. It didn't seem to add too much. So I'm basically going to try to generate the image I got yesterday. And we'll kind of go from there. It's a language like any other. You wouldn't learn Russian overnight. Why is this happening? Let's try removing the density estimation real quick. And let me see what's going on. Include ifs.jl. Shouldn't take too long to run. Oh, I know what's going on. We're generating fewer points. Okay, so let's go ahead and generate this guy, and then we'll generate the same guy with density estimation, and we'll see if we can find a difference here. So here's a fractal.png. Okay, so let's go ahead and move fractal.png to fractal no dense.png. Okay, and now we're going to run this again with density estimation. Include ifs.jl, and we're going to see if we can find a difference. Now I increased the gamma so we can more easily find the points on the edge. And we're going to try just a bunch of different density estimator guys and see how it goes. What does competent mean? Okay, so here we're going to do mirage fractal.png. I guess I'm also going to have, where are we? So here's fractal, and here's fractal no density estimation. So here's our fractal with density estimation, and it doesn't really look too much different than the fractal without density estimation, if I'm being honest. All right. Nice. Come on. All right. End process. Let's try that again. Here's a fractal with density estimation, and here it is without density estimation, and I think it looks almost the same. So to change, let's go ahead and change the fudge factor then, and maybe the size of our plot here. So we're gonna change this to be, what do we want to change this to be? Actually, let me also do one more thing. So we're gonna increase the size of the Gaussian filter to be a lot larger. And let's go ahead and go up to the density estimator here. And I'm just gonna change the one thing real quick, because I realize we're doing 1 over sum in the define filter. But it could potentially be that this sum is 0, so I'm just going to go ahead and change this to sum plus 1. Okay. And it could be, there could be a lot of problems here. I'm not sure what all the problems would be. So let's do 1.0. What do we have here? What kind of fractal is the first picture? It's just a combination of different fractals. So what we're doing here is we're doing the fractal flame method, right? So the idea is that we are combining a bunch of different fractals together. So this is kind of like a bunch of different fractal flames. It's, I think, linear plus swirl plus one other thing or something like that. The state of Florida requires 6K hours of field time to set for my master's. Oh wow, that's a lot of field time. Let's see. You don't need 10,000 to be good at something, but to be an expert of something, you need 10,000 hours, or maybe not. Well, yeah, I don't know. It again depends on how those are spent and all this kind of stuff. Nice question. What do we have? Best fractal zoom ever? Oh yeah, I don't remember this. Oh no, I do remember this. Oh yeah, that's a tree. Alright, what are we going to do? We are going to change this down here, G, and let's increase the number of points here to 1,000. So what I'm trying to do then, yeah, let's increase this to, I don't think it's that many, right? So we're only generating, yeah, let's try 1,000 here. Okay, let's go over here and let's do Julia ifs.jl, and let's give it a go. Let's see. Although I'm going for a robotics master's in Florida, and I've done laughably little actual field work. If you spend 10,000 hours coding with the knowledge of if, else, and for, and never learned about functions, well, you aren't a master after 10K hours. Yeah, that's also fair. I just increased the computational complexity of this by a lot. So give it a second. All right. Let me check my side chat over here. Let's see. Yeah, okay. For some reason, Google just sends me notifications that seem really urgent, but they're not. I don't know. So I don't like smart devices. I prefer just to have the second monitor. Did you ever think about getting into machine learning and stuff? Yeah, I have. Obviously, I think everyone at some point thinks that they want to get into machine learning. Sorry about that. The issue is that when it comes to machine learning, I just haven't had a good reason to do so. It's not it's not something that's yet been useful to my research career. I get a Google Scholar notification for James Schloss. Oh, did you? Huh, let me see, what do we have here? Google. I didn't. I'm hoping. That's my GPU paper. No, it's this one. Ha! It's just an archive preprint. The GPU paper isn't out yet. Ah, fine. I'll have to add that one in manually. That's okay. Alright, come on. Julia, do your thing. Let's see. Wouldn't that mean every link that goes on his Twitch channel would do that? Could be. I'm not really sure. I've been doing a lot of machine learning lately. Yeah, so machine learning, again, it's something that I do want to get into, but I just feel like I haven't had the reason to do so yet. Just watch out for the water rising. I have just seen a TV documentary with movie stars, I think, about climate change. Then how can you ban the climate change? I see what you're saying. Yeah, that's true. Like, in the US, there's a lot of people who just genuinely do not believe climate change is a worthwhile endeavor to, I guess, work with. You know what I mean? Like, it's just not worth looking into. By the way, guys, if this density estimation doesn't work by the end of the day, I'm kind of happy with the fractals we're already generating, like this guy here. I'm kind of happy with that. I mean, I realize, yeah, we should have density estimation on top of this, but I'm genuinely happy with this fractal, so I'm okay with just like using this. Does that make sense? Like, I don't really need the density estimation. It's just the final step of the fractal flame method, so I figured since we're here, we might as well implement it. You know what I mean? They didn't ban using the word climate change from all They banned using the word climate change from all political meetings. Yeah, I kind of know what you're saying. It is a pain in the butt. The fact that scientists are not being listened to in Congress, I mean, it's a huge deal, you know? And I genuinely cannot stand the anti-intellectual sentiment that is rising in the US and several other places around the world. It's always been there in the US, but there is no Christmas tree in the picture yet. I have not yet generated the Christmas tree fractal. We spent all of the past 3 days, well, Saturday, Monday, and Tuesday, we spent just kind of updating the fractal flame method. And from there, we're going to be working on basically generating our fractal. So the idea is that we work starting with the Barnsley fern, and then we add some additional oscillations or some additional fractal flames on top of that to make it look better. But I do think that we're going to have a hard time beating the Barnsley fern that we were generating at the start. I think that Barnsley fern is probably the best we can do. I can probably change the background of a new plot to be black. There's probably things that I can do to make it look better, and I'll try to do that. This is taking a lot longer to run than I was expecting. The Christmas tree fractal? Yeah, we're working on the Christmas tree fractal. We're trying to create a Christmas tree fractal, but so far we haven't done it yet. I've gotten a few submissions from people who have also generated Christmas tree fractals. So if you generate a Christmas tree, it doesn't have to be via a fractal. If you just generate a Christmas tree in code, feel free just to send that to me, and I'll put it in the next video, which should be out on Sunday. Let's see, C252 courses on Coursera are free actually, but if you want to take the quizzes and certificate after you finish the course, you need to pay a bit of money. Yes, fair. See, like this, if humans don't do something against climate change, all the dumb humans die, and the clever ones too. The US has more of an ostrich approach to real problems. Put your head in the sand? Yeah, I understand this. You did a tree in another stream? Yeah, I've been trying to figure this one out. So this is just taking too long to run with the density estimation, so I'm just going to Control C here, and I'm going to change this to 20. No, let's just keep it at 10, actually, because I don't remember this taking that long when it was at 10. So let's do include ifs.jl, and let me see how long this takes to run. In fact, let me just do a Control C here, and let's do at time. Include ifs.jl, and let's see how long this takes to run. I have no idea. I don't think it should take that long because I remember doing this just a second ago and it was fine. But the problem is, this is some weird like end of the cube thing. So that took 12 seconds. So let me increase this to 2. And let's also time include that guy. And we'll take a look at this image in just a second. I've got a feeling this will take a minute or two. Let's see, 2:20. We increased it a factor of 2, so it might take 8 times as long. So it might take a minute. Let's see. If you haven't heard about Coursera before, you should have a look at it. A lot of good courses, and you can audit them. Yeah, that's fair. Oh, it only took 20 seconds. Interesting. Okay, so let's take a look at the image that we have here. We're on fractal.png. And again, this is, oops, sorry. They're looking about the same, if I'm being honest. Let me zoom in here, and let me see if I can find any difference between these small scale objects. Oh, gosh. Yeah, this keeps freezing on me. Come on. Pain in the butt. Is it possible you hit a memory? Yeah, I've hit a memory limit before. But maybe not, I don't think with the run I was running before. Come on. There we go. So let me try that again. We're on Fractal.png. Yeah, I'm really not noticing too much of a difference between these two. They're both just about the same. Let's see. So here's Fractal.png. Okay. And here is the fractal without the density estimation. I'm really not noticing a difference. What I was hoping was that we could see kind of these guys over here more smeared out with the density estimation, but it just doesn't seem like that's the case. So let me increase this to 10,000. And let me just try running that. ifs.jl. Is it possible to burn your GPU while doing GPU coding? It is actually. Yeah, So let's go ahead and quit here. And actually, let's run this again. Let's increase this to 50 points, because it didn't seem like it changed that much. So let's change this to, yeah, it takes 20 seconds here. So if we increase this to 50, yeah, we'll give this guy a go. So we'll go ahead and time that guy. And while that's going, let me run htop, just to see what's going on here. Clearly it's not parallelized appropriately, because we're using 100% of one core. But our memory's fine. It's only at 4 gigabytes. So we increased this by, we doubled this again, and then added 0.5. So I'm gonna guess this is gonna take about a minute to run, and we'll see how it goes. One of the zip ties on my computers. Wait, what? One of the zip ties. Oh, zip ties. I misread that. One of the zip ties on my computer started to melt one time when I was using it. Yeah, this has happened before. But I had a friend of mine, actually the previous developer of GPUE, he actually did burn out a GPU before. While running his code, so it does happen, but it's usually via GPU computing, not via gaming. Because GPU computing, you'll be using your GPU at full throttle for all the time, So it's one of those things that it is possible to burn out, but it doesn't happen that often with passively cooled GPU cards like the K80 and stuff like this, because usually these are cooled by some supercomputing cluster or something, so the cooling is much better. If you showed a picture of my old GPU, you'd be terrified. Okay, so 71 seconds, that's not so bad. Let's take a look at the image, fractal.png. And honestly, guys, I'm sorry to say, but I'm really not seeing much of a difference between these guys anyway. Fractal no dense, fractal dense. They look almost identical too. Maybe we spent all this time with the density estimation for nothing. So let's zoom in here again. So here it is with density estimation. And I'm really just not seeing, I mean, maybe in here or something? Here is without density estimation. Yeah, I'm not really seeing a difference at all. That's without density estimation. Let's move on to with density estimation. Oh, well, maybe. Maybe in here, it's a little bit blurred. It's probably just because these are single pixel objects that it's kind of hard to see anything with. Yeah, so maybe the resolution of our image just isn't really high enough that we see anything with density estimation. Maybe that's the problem. Maybe because of how we've written this code, or maybe just because of the size of the image that we're outputting, or something like that, we're just not going to be able to generate anything that density estimation really helps with. Oh. You ought to run a web server virtual machine on flash drives if you want to cook some dinner. I made some smoke once. You take analgin and hydrogen peroxide. It'll smoke in about 10 minutes. Huh. OBS got quite some threads. Yeah, OBS takes a lot of power. Are these fractals using 8 gigs of RAM? Something like that. I'm not really sure. We could do a larger image, but I mean, as you saw, it just takes forever to generate this stuff to begin with. So we could do some parallelization, but as I said yesterday, I'm not really sure how to do the parallelization. I would love to do a GPU stream on this, but I just don't know how to do that. So I'm gonna have to take some time to kind of think about this a bit. So for now, I think maybe we should just move on to generating different fractals, and we should drop the density estimation for now. Maybe mess around with the intensity of the filter. Yeah, so I did, right? So what I did, just a second ago, let me just go ahead and clarify, is I modified the density estimation basically so that the fudge factor is 10,000. So what this means is that, let me just go ahead and show where we're defining the Gaussian. Where's the defined Gaussian? Function density. Here's a defined filter. What this means is that our fudge factor is going to be 10,000 over whatever we sum. So the idea is that the sum that we're putting in is always going to be less than 10,000, which means that our filter is always going to be very large, right? So this means that we're just kind of using an incredibly large Gaussian filter, right? So this incredibly large Gaussian filter is just kind of mopping over all of our objects, right? And it's on this huge 50 pixel radius, right? So it's this huge 50 pixel giant Gaussian smear tool that's just going over our entire system, you know? But for some reason it didn't really do anything. So maybe you're right. Maybe there's something wrong with the, maybe there's something wrong with something in here. Maybe the filter itself, Maybe we're casting something onto an integer at some point. Let me just output the filter at one time step here. So we're going to say print line, and we'll just say filter, right? I'm just going to run this once, time include ifs.jl, and we should output the filter in just a second, and I'll just cancel it the moment we're outputting the filter. Okay, so it looks like the filter is filled with doubles, so there isn't that big of a problem here, but it also looks like it's quite low, actually. Maybe our issue is that this Gaussian filter is just too small. So these are doubles, so that's one problem solved. Let's try increasing this by 10 or something like that. So this should automatically be. So this should let's increase this by 100. I'm just messing around with numbers now just to see what we get. So I'm increasing this by 100, and then we'll let it go. It's going to take a minute, and then we'll take a look at the image. And again, what we should be seeing is this giant just mop just going through our system. We should see something that's super blurry, and then we're going from there. Fulter, could you link your YouTube channel? Yeah, please do, actually. I'll go ahead and subscribe to it. I think the density estimation is implemented semi-correctly. Like, I'm not too worried about it. Leos' YouTube channel. Thanks, JSPP and Simbot. Okay. Oh, no, don't worry about it. It's fine. It's clear. 12:21 a.m. for me. Gotta get some sleep. Enjoy the stream, people. Thanks so much for coming in. I'm Not Swak. Have a wonderful day, or a wonderful evening, and hopefully I'll see you around later. I should rechat. Sorry, hold on. No big deal, man. So this should take, again, about 70 or 80 seconds. So it should take about a minute. I'm gonna get some water real quick. But yeah, like I said earlier in the stream, in 2019, I really do want to put more content out. Yeah, 72 seconds. Let's take a look at the image. Yeah, again, it's looking the same, but this doesn't make any sense because, like, we are literally moving through this image with this giant paintbrush that is just this huge Gaussian filter. Like, we should be blurring it a lot, but it just doesn't seem like we're doing that. Interesting. Let me take a look at the Julia that we ran last time. So this was 0.00. So basically I increased all of these guys by 100, right? You know what's super interesting about this? Holy crap, I just realized this. All of these numbers are the same. 0.00398864. What's going on? Why are they all the same value? That would explain why we're not getting anything crazy, but why are they all the same value? We're saying the filter of I, j is equal to 100 times 1 over the square root of 2 pi sigma times exp of negative x squared minus y squared over 2 times sigma 2. Why are they all the same value? I'm wondering how many nationalities work on the algorithm archive. I assume a lot, because very few people are from the same country. I think the largest number of people, I mean, maybe we have a few people in the US, but I know we also have a few people in Germany, so let's see. All right, looks like sort of half destroyed. Yeah, why are these all the same value? All right, so that's something I got to figure out now. The filter itself. Would they all be the same value if... No, I don't know why they'd all be the same value. I know me and Berquist are in the US. I mean, technically I'm from the US too, but I live in Japan, so I don't think we have too many people working on it in Japan. Oh no, we do. We have a few people working on it from OIST, but they're all just friends of mine. So, let's see. Filter. I doubt that we have much outside North America, Europe. Would be cool. If not, though, we have. I mean, we have a few people from India. I know that, but I don't know who else we have. India, actually, I've got a lot of people from India that watch my channel. So there's quite a few people there that are interested in the algorithm archive. Let's see. So we have exp of negative x squared minus y squared. Am I doing something dumb with this x squared and y squared guy? Maybe. I'm just going to output x and y here. So let me just print line x and y. All right. X, y. All right. Let's just see what we got here. So we're going to time this guy, let it run, and I'm going to see what's going on with this x squared and y squared guy, because maybe there's something really weird going on. Let's do a quick control C here. And it looks like negative 1.92, the y value is constantly changing. So it does look like we are appropriately changing x and y. All right, so that's not an issue. Is there something wrong with this this exponential guy here? So it's 1 over square root of 2 pi sigma 2. Should be fine. Minus x squared minus y squared. Oh. Maybe. No, that should be fine. Should be minus x squared minus y squared. That should be correct. I represent in the Netherlands. Ah, nice, thanks. I know a couple people who have popped in Discord were Russian. I think Nev was the only contributor I know who's Russian. Yeah, fair enough. I also think there's contributor-wise. I've searched some trees. Let's take a look. Oh, yeah, this is fair. You have a whole bunch of Christmas trees here. Open link. Open link. Oh, that one's quite nice. Yeah, it's way better than whatever we did. Create fractal tree. Yeah, so this one, I think someone submitted one that looks a lot like that. And this is just... Yeah, see, these are better than... the fractal flame method. Maybe we're barking up the wrong tree here. Yeah, maybe we are barking up the wrong tree with the fractal flame method. It doesn't matter too much to me. I'm okay with just using the Barnsley-Fern stuff that we had before. I mean, it doesn't have to be that big of a deal. Honestly, what I could do is I could just put the Barnsley-Fern stuff that we have up already, explain what this is, explain how it works, and then after that, just say this is where we tried. We tried using the fractal flame method, spent a lot of time on that, and just didn't pan out. You know, and this is fine by me. I don't mind that. Because if it doesn't work, it doesn't work, and it's okay. I don't mind so much about it. I don't like beaches. Open link. This is your channel, right? Am I already subscribed? I am not. You are now subscribed. All right. Let's see. This is my channel. No content on it yet. I don't know. How do you add all those globes and stars, color things? Yeah, it's fair enough. There's definitely ways to do it. I'm not so worried about that. We can do it without too much trouble, even just with new plot or something like that. It's not so hard. Yeah, I don't know. Maybe the thing is, this doesn't necessarily have to be Christmas themed. It's just almost made the first subscriber. I'm sorry. Okay, so there's something clearly wrong with this filter. But I don't know what the deal is or what the problem is here. So we're doing x squared minus y squared. This should be fine. It should be some sort of two-dimensional object. So how about we change the filter again to 10 by 10? We output the filter. I just want to take a look at it real quick. So we're going to do 10 by 10, and let's just go up to define filter here, and we're just going to take a look at it. So we're just going to say print line. All right, so we're going to include this guy, and we're going to give it a go and see what it looks like. James beat me to it. Yeah. I think a lot of people just, I mean, not maybe too many people. Control C here. Well, now that's weird. The first line is 0.39884. They're all 0.39884. Well, what's going on here? There are some small scale variations, 3.9884, 3.9886. Like, they are changing. Seems fine. I guess. But then down here, what's going on here? It's 0.39884. Then the next one's 0. Why? Is this because... Is this because there's no points in that filter area? Oh, no, I think I know why. I think I'm filling up the filter. Yeah, because I'm printing the filter at the wrong place. Let me DD here. Let's paste there. Let's try it again. Let's see. I still have the title of filters for a Twitch viewer. Nice. All right, so these are all basically the same though. 0.39884. They are changing very slightly, but not enough. Why? Why are they all basically the same? Oh, this means the sigma is very large. That's why. Okay, let's pop down here and let's drop this down so it's actually a Gaussian. Okay, so now let's try include this guy. I think I know the problem now. Serve that. Yeah, so I think I understand the problem. The problem was that the filter was so large. Control C. Yeah, so this is clearly different. So here we have 9.6, 8.495, 12.5. Yeah, so let's increase this, drop this to 1.0. Try that. I like the number 252. Also, C. Fair enough. Control C. Alright, it goes from 3 up to 28. Yeah, this is basically what I was expecting. 0.79. Yeah, I'm okay with this. So let's change this again to 50. And let's see if we see anything now. So I'm going to go to not print out the filter anymore. Where's the Sierpinski flame? Where is it? Here's density estimation. Let's go ahead and not print out the filter. Let's include ifs.jl and let's see what happens. It's not a dumb name. It's fine. There's nothing wrong with it. I mean, my name's Simuleos. I mean, that's a pretty hard name to follow at all. It doesn't matter. I made a trash email and put talk after it so it became a different word. That's probably one of my favorite origin stories I've ever heard. Like if the Marvel Cinematic Universe had this as their story to start like a superhero with, it's like, yeah, I want to be called Trash Man, but apparently that name was already taken, so I can change my name to Trash Talk Man 217. Oh man. It's pretty good though. I'm a fan. I'm gonna get some water real quick. Man, superhero Trash Man. He's my favorite superhero. Keeping the streets clean of crime since 217. It's probably prime. 2 plus 1 plus 7. Yeah, that's pretty cool. 2 plus 5 plus 2 equals 9. That's also pretty cool. It's off by 1 from 10. So, you know, you always do a loop from 0 to 9. So there you go. You're there. Let's see. This is taking some time to run. I'm not sure exactly why. So... yeah, I hope everyone's having a wonderful day. Thanks for sticking around with this density estimation endeavor, which may be completely useless now that we're looking at it differently. Let's see. Have you tried some super strong black tea? Actually, no, I don't very much like black tea. It's got a little bit too much caffeine in there for me. I don't drink any caffeine, actually. My sister used to have like heart palpitations when she drank too much caffeine. And I don't know, since then I've just been not terrified. I just haven't been wanting to drink anything with caffeine in it because it's not something I drink normally. And I just kind of realized how bad it was for you. And I just haven't done it since then, you know? Same is true for a lot of different things. 122 seconds. So it took a lot longer to run. Okay, so let's run Mirage Fractal.png. It took a lot longer to run, and I'm really not seeing much of a difference either. Here's Fractal no density. Here's Fractal with a density estimation. And we know that the filter is being generated correctly because we just took a look at that. So we are generating appropriate Gaussians for the filter. It's just not really changing very much here. Here's the Fractal.png. Let's zoom in a bit. Yeah, it's not doing very much. I mean, there's some small scale variation here. Zoom in again. Nah, I'm not really noticing much of a difference. Still, this is probably the best one that we have so far. And admittedly, I don't mind having these points kind of on the edge of our fractal flame method so much. I think it's perfectly fine. I'm just a bit bummed that it didn't do more than I was like, it didn't do more. Yeah. Let's no longer multiply it by 100. Let's just try it one more time. Just do regular old Gaussian. I'm just gonna pop down here and let's change this to... Nah, it should be okay. So let's just go ahead and run this one last time. We'll give it a go. If the density estimation doesn't work, it doesn't really matter, right? So like I said before, because we have the Barnsley fern, that kind of sort of looks like a Christmas tree, and I'm okay with that. I'm pretty happy with where we're at so far. I mean, of course, we can add just like little ornaments and stuff to the Barnsley fern. But what I can do is I can mess around with the Barnsley transformations just to make it look a little more Christmas tree-like and, you know, a little bit nicer here and there. And then we can just say, hey, look, we generated like, or I can describe what the Barnsley fern is. I can make it look Christmas tree-like. You know, like, here's the thing. Worst case scenario, we still have the Barnsley fern, which is still a very interesting thing to talk about. Don't get me wrong. Like, we can show all the transformations, we can explain how these work, all that kind of stuff. And then we can say, hey, since it's Christmas time, this kind of looks like a Christmas tree. We asked for the community to generate fractal Christmas trees, and we tried our hand at doing the fractal flame method. It didn't really work, all this kind of stuff. That's fine. And so I think ultimately, even if we didn't really do like if the stream fails and we don't actually get like a real Christmas tree generated with the fractal flame method, I think this is okay. I don't mind it so much because, you know, we can still talk about it and it's fine. But 217 is fine. Everything's fine. Let's see. 7 times 31 is 217. Why couldn't I have been more clever like 4 years ago? Man, tell me about it. Like, man, why couldn't I have been more clever like 4 years ago? Why is the name... Do real Christmas trees use Emacs? Yeah, this is true. Did you finish the cow animation? No, we're still working on the cow animation. There's a lot of things we're still working on. It's just that since this weekend is Christmas, or rather, next Monday is Christmas, I thought we could try to draw some Christmas trees and stuff like that. But ultimately, I'm pretty happy with just talking about what we did during ThinkerCon and describing, you know, how we can take it a step further with the fractal flame method and all this kind of stuff. But also, I think maybe just putting a video out, just saying, you know, we tried to generate our Christmas trees and stuff like that. I think that's fine. So let's take a look at the image here. Mirage fractal.png. Yep, I'm noticing no difference, like literally no difference. So I'm gonna sit here and I'm gonna say we have the density estimation. I want to say it's working, but I really can't tell, you know? It's taking forever, so it's definitely doing something, but it just doesn't seem to be doing that much, you know? So I guess what I'm going to do here is I'm going to say, I'm just going to go ahead and commit what we have. So git add ifs.jl, git commit -m. I'm adding density estimation, but it doesn't seem... And I don't think it's going to be doing that much anyway, because the points that are super sparse, like the points that are super far away from each other, I'll show you what I mean in just a second. So these points up here that are super far away, I think they're just too far away to kind of gloss over. Like they're too far away to blur. So what I'm going to do real quick is I'm going to read that image into Julia. And I'm going to try to see if we can do anything here. So let me move over here, and we're just going to say into Julia, we're going to load. I guess we're going to have to use using image view and using images. And then we're going to load it in here, and we're going to see. I visited a Christmas fair last weekend. They were playing rock music, getting those Christmas feelings. Is there such a thing as rock? I guess there is Christmas rock music, I guess. Okay, so we're going to do load fractal.png. And then we're just going to view it real quick just to make sure it is loaded in. So we're going to do im show. And it's going to be... Oh, oops, I forgot to do something. img is equal to load fractal.png. And now we're going to do imshow img. So here we showed the image. Christian rock music. Honestly, I don't mind Christian rock music. I think it's okay. Like, I think it just gets a bad rap. But I don't think it's that bad, honestly. Jingle Bell Rock? Yeah, that's fair. Jingle Bell Rock. Yeah, okay, so here's the image we were just looking at. Looks fine. So now we're going to put a Gaussian blur on top of that. So let's go ahead and do, let's see. Actually, I can probably find it this way. imgg, imfilter, img, Gaussian 0.5. Let's take a look at what we have. What's Christian rock music? It's just like Christian music, but it's Christian rock music. It's pretty good. Yeah, so here, I just put a Gaussian blur on top of that, and as you can see, there really isn't much of a difference. Like, I just put a blur on top of that, and it's very hard to see. I mean, let me go ahead and put a larger blur on that. So Gaussian of 1. And let's do imshow imgg. See, here we can see the blur, but if I zoom in here, like, honestly, the blur isn't even that useful. You know what I'm saying? So this was a huge blur associated with it. And it also just makes the whole image look worse. You know what I'm saying? So, like, don't get me wrong. It does kind of help out in these areas here. But ultimately, I think it's not worth it. So here's, oh, oops, that was an oopsie doopsie, as they say. So let's open up the image next to it. Okay, so here are the two images put together. I'm just going to zoom in here. So here's one and here's the other. I mean, again, we're using a very low number of points here. So let me move up here and let me move up here. Yeah, I do like this a lot better than this. Like, this is just pixely. It's too pixely. Move down there. Move down here. For this number of pixels, it doesn't really matter that much, I guess. I mean, maybe we could just do... Nah, but I still think I like this one more than this one. You know, this is just too blurry. This one looks kind of nice. But even so, even on this one, you can still, from a distance, it still looks like we have all these pixels on the outside. You know what I mean? Like, it doesn't change the image that much. All right, so I'm just going to say I think we did implement density estimation kind of, sort of okay. But I think that there's an issue with, I don't know. I don't know what the issue is. I mean, that was just a large-scale Gaussian blur that we put on the system, right? And that was okay. I mean, we can add a blur to the system. But I think maybe the density estimation is just too computationally costly to do for this particular system. Maybe. I don't know. Let's see. Chaos Theory 34, thank you so much for following. I apologize for missing that. I would probably rather hear Last Christmas in an endless loop. I like Christmas music. I don't know. It's fine. This fractal could be a Christmas tree from above if it would be a bit more symmetrical and make some colored stars at the end or something, and then generate a forest with these trees. It's pretty sweet. It's a crop circle. Then again, I wouldn't know this flare works. Yeah, so basically the fractal flame algorithm is a method of combining iterative function system fractals. So like the Barnsley fern is an iterative function system fractal. You mix it with other fractals and you get fractal flames, which are just kind of a mixture of a whole bunch of different fractals. Yeah, I mean, blurring it in GIMP, yeah, I mean, ultimately, like, looking at it this way, I think is also fine. Let me see once we generate an actual fractal here. So I'm going to do img is load fractal. I think it's high many point.png. So I'm going to load this guy, and I'm going to perform a Gaussian filter on that guy. All right, and now let's go ahead and take a look at these guys. So here's, this is probably fine. I'm show imgg. So here's one of them. And let's do img. Here's the other one. Yeah, so between the two of these guys, I think there's a clear, I'm clearly favoring this guy over this guy. This one just looks blurred, which is what I did. I just added a Gaussian blur to it. It's probably hard to see on stream, but I don't know, there's advantages and disadvantages, but ultimately, like, the fractal flame method, it's not exactly clear, like, what it is that is the fractal flame method. Like, you do the fractal flame, and then the rest of it is just post-processing to make it look better. And so ultimately, I think I'm happy with just generating what we have and not necessarily doing too much with the density estimation. I mean, I could add the density estimation there, and I think it does help a bit. So I think for the final plot, I'll add in some density estimation. But I think for now, while we're just testing, I don't think we need it. Oh, okay. So, I'm sorry about that. I'm yawning. I'm happy with what we did today. I think we did implement it correctly. I just think that the plot itself isn't as, I guess, dynamic or as crazy as we were expecting, you know? So I think this is okay. I think we did what we needed to do. And so now what we need to do tomorrow is basically just play around with a bunch of fractals and try to generate something that looks more Christmas tree-like than whatever it is that we were generating today. So tomorrow we can do one of two things, and I'm going to ask you guys what you think is best. So I need to do one extra visualization for the video that's coming up. And basically this visualization will be generating a random number of points and using and transforming all of these points with our basically Barnsley-Fern transformations. So the idea here is that we generate a bunch of random points and then we show how they move depending on each of the transformations. And I think that this will give us a good intuitive feel for what it is we're doing with each of the different fractal flames. So I kind of feel like I want to do that tomorrow. Just quickly hop into GathVL, generate a bunch of random points, show what happens when you move these points together, and that's basically it. Nothing crazy. And then I think I'll do that tomorrow, and then on Friday we'll come back and we'll work on the Christmas tree stuff. Maybe also on Saturday, we'll figure it out. But ultimately I need to get this video all recorded up and ready by Friday night. So I think if we get the animation done tomorrow morning, then I can work on the Christmas tree from Friday and Saturday, and then whatever we finish Saturday after stream, that's what we're putting into the video, so that I can just say, hey, here's the best we did with the fractal flame method. It didn't turn out as well as we wanted, or it did turn out very well. I don't know, it depends. So that's kind of what I can do. So I can get the video ready to go, so I can just put the image in at the end. So that should work pretty well. Okay, cool. So I think that's it for the day, guys. We implemented the density estimation. So tomorrow we'll come back and we will basically perform our, or do a quick animation so that we can figure out how the Barnsley fern works exactly, so that we can kind of modify our fern and make it look more Christmas tree-like. Then we can go from there. So I think this is it for now. Let me go ahead and take a look at who's online on Twitch. Let's see. So, Oh Bother's live. I usually really do like hosting Oh Bother. He's such a nice guy. So I don't mind hosting him again if you guys are okay. But also Skylius is live, and I'm a fan of raiding Skylius. They're fine too. Does anyone have a preference for who we raid at the end of stream? If you do, let me know right now. Otherwise, I will go ahead and just raid. Should it be Oh Bother or Skylius? I feel like we always raid Oh Bother, and we very infrequently raid Skylius. Let's see. Who's Skylius? Skylius is a Oh Bother. So some people want Oh Bother. That seems fine. Skylius, she is a streamer. She does educational stuff. She's actually one of my favorite channels on Twitch. She basically just talks about space and stuff all the time. But if everyone wants Oh Bother, that's fine. We'll do Oh Bother. And I think that is it. So thank you guys so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it has to be your time. Danator. I don't know Danator. Let's take a look here. Danator. Oh, it looks like they just went. Yeah, it looks like they just turned off. Okay, so we'll do Oh Bother. Thank you guys so much for coming in, and I will see you next time. Bye, guys. Yep, that's my outro now.